Ben Hamlin here. He's a research engineer from Galois. Is here to talk about leveraging Rust on the core platform. Oops, the micro-kit. Sign of maturity as names change. So go for it.
I don't actually know how to full screen this, so you'll have to live with my browser window, I guess. So I excuse me. We've been working on porting a native Rust network stack to SeL4, and also doing some assurance on it. I won't really talk about the assurance. I think Michael Podrosky is going to talk about that a little later on. But yeah, so we've been doing that and and using the microkit Rust interface. Like, I guess I'm going to talk to you a bit about our experience doing that. Like, really, what I'm going to talk to you about though is I guess like it's dual purpose. It's both our experiences and like a design pattern we ended up coming up with that seems to work well for reusable driver code specifically. I guess first though, just to like set expectations, my background is not in operating systems or embedded systems or even formal assurance. My background is I'm a cryptographer by training. I ended up on this project at Galois because I am pretty comfortable with Rust. I've implemented a bunch of cryptography in Rust. Yeah, so I didn't just wander into the wrong conference. Right, and then like also, so like I mentioned that I'll be talking about are implementing or porting of a network stack and device drivers and microkit and Rust all on SeL4. That's like a SeL4 Summit bingo maybe, but like I'm not going to be wowing you with amazing network driver code. It's really just mostly this design pattern that we came up with or like decided upon. That hopefully will be pretty like simple, verging on the obvious. That's like my hope. My hope is that you find it really obvious. If you don't, I'll assume that I didn't explain it very well. But yeah, so I guess without further ado, so our motivation was that we wanted to, as I say, like adapt this existing Rust network stack, small TCP, if you know it, to SeL4 using microkit, but we wanted to do it in a way that was reusable in the sense that like there are a lot of well, there are some hardware drivers out there already written in Rust, and you know, a fair amount of application code that knows how to use existing Rust hardware drivers. And so like this is the setting we were interested in, where you already have like let's say a Rust crate that contains the code to talk to your hardware, and you already have like maybe not a full client application or maybe a full client application, but anyway, at least some like library code packaged up in one or more crates that knows how to talk to a more traditional driver. So sort of looking at the way you do this in microkit, and by the way, I feel like my like the fact that I was able to get going on this as fast as I was, or even at all, is kind of a testament to how like usable I found microkit. the interface was really great, and Nick's documentation was awesome. But like the process to do this definitely involves some work. So like where you would start is like, the driver and client need some way of talking to each other, and so you would design a protocol using like the protected calls and notifications that I think you saw in one of Nick's slides, or maybe Yvonne's, or both actually, to have some kind of communication between the driver and the client, and also probably you want some shared memory, or like quite possibly you want some shared memory. So all of that sort of combines into a protocol that the driver and client use to talk to each other. And so once you've designed that, you have to take your existing driver code, or your crate that like knows how to talk to the hardware, but maybe only presents a more like standard rusty interface to a client. You have to sort of adapt that to be able to speak this protocol you've designed. And then on the client side, similarly, you have to take the libraries that you have and make them speak this protocol. And maybe you can do that with sort of a wrapper around the libraries, or maybe you have to like dig into the libraries to do it. Anyway, it seems like it involves some work. And then like once you've done this, like it's maybe reasonable to take the protocol you've designed and like wrap it in a crate itself, like some kind of interface or adapter. So that the next time you have a driver and you want to talk to a client, and they have the same kinds of interaction, right? Like it's the same kind of driver. You don't have to rewrite this protocol, but still we haven't really given away to reuse the code that we wrote to get the driver to speak this protocol, or to get the client to speak this protocol. And so I guess really like the question we were asking was, what's the best like thing to put at this interface boundary, or these two interface boundaries? So like one reasonable thing to ask would be, how is this already done in Rust? And so for many drivers, the answer is this embedded-hal trait. HAL stands for hardware abstraction layer. The idea is that this is a crate or collection of crates that provide traits, Rust traits, that sort of give you an interface to an interface to drivers, and the idea is that it's supposed to be kind of hardware agnostic. Like the thing using the driver shouldn't have to worry about what hardware it's running on, basically. I guess like probably many people already know what Rust traits are, but just in case you don't, they're I mean, it's just an interface of methods, mostly methods, that you implement on a data type, and then you can make your Rust code polymorphic over things that implement that trait. It's like interfaces in Java, although the traits themselves can be polymorphic, or also like type classes in Haskell, if you know Haskell. I guess again, I think there are some differences there. My PL friends tell me that Rust traits don't support higher order polymorphism, but I don't know what that means. I'm sorry, higher kinded polymorphism. I really don't know what that means. Right. So yeah. So what does this look like? Well, the way this normally works in like again a more traditional system is that again your client has like a hole in it where a data type or like a struct representing your driver would go, and the shape of that hole is represented by some trait, possibly in the embedded-hal crate, or there are some others. And then your driver just implements that trait. So like here, for example, it's a serial driver, and it's existing some like common. I'm sorry, it's implementing some common serial driver trait, and then that's the interface that they share, right? And there's this nice like clearly defined interface at the or clearly defined abstraction at the interface. So how can we take what we had before and make use of that? Well, again, my hope is that like it's obvious and you already see it. But so like really we can just take this crate and let it pretend that it's a normal client of the driver. So oh right, and again let's assume, for example, that we have like in the like on the previous slide, a driver that implements this existing serial trait and a client that knows how to use something that implements that trait. So so we'll just take this this crate and make it pretend that it's a client to a Rust serial driver, and then we can write code that encapsulates our the protocol that we're using to communicate between the driver and client. But the point is that the driver doesn't have to worry about that communication code. It just, and in fact, if your driver already implements this existing serial driver trait, the code for your driver protection domain should be like almost nothing, because you just like plug it into the hole, right? And similarly, since our client already knows how to use something that implements existing serial driver trait, we can just provide a struct that implements the serial driver trait, and make it speak this protocol as well, and then just plug it into the client as is. So like this is basically it. Again, hopefully it's very unsurprising. But so like let's look at a couple of examples of it. So we tried this out with a serial driver, and so this is the driver's view, in the sense that it's like what's inside that intermediate adapter crate, right? And as mentioned, we have this serial handler. So this is a I feel like I should have had a slide on this. So like I guess Nick already did sort of like the way you implement a component in MicroKit, or at least one way, is to have this protection domains init function, which returns a handler, and the handler the handler implements this handler trait, which tells it how to handle protected calls and notifications. So that's it. So we're just making a generic handler for serial devices. So it's a struct, and it takes a device as a type argument. And then this part here is just saying that if the device implements the embedded-hal serial read and serial write traits, then the handler implements the SeL4CP, the microkit handler trait. So, well, and yeah, I guess this code is, I'm dating myself with this code. It's 3 weeks ago, but yeah, I should have just run the tool. So here's what this looks like inside the actual driver component. So this is the initialization function, and you can see all it's doing is instantiating some handler that's I'm sorry, instantiating some device that's defined in an existing crate. In this case, the PL011 device. And because that already implements the serial read and write traits, we can just use it to instantiate a serial handler, and we're done. This is the entire code of our driver. Then what does it look like on the client side? Well, similarly, so we're back inside the adapter crate. So you know, there's a fair amount of code to write here, but the idea is you only have to write it once, right? So you have a serial driver struct, and it implements the embedded-hal serial read and write traits, and you can see in the implementations of those traits, it's you know, using protected calls, maybe notifications, maybe shared memory. It's doing all this like stuff to communicate between the two protection domains, but it's all encapsulated in this adapter. And then when you actually go to use it, excuse me, in the client. So I mean, this particular client maybe does some more stuff. I like it. It's not just a client that instantiates a serial driver. It probably does some stuff with it, right? But as far as the serial driver is concerned, this is all it needs to do. It instantiates the serial driver with a channel, and then when it uses it, it just uses it with the same excuse me, the same macros that it would use to interact with a sort of a native Rust serial driver. Is native the right word? I'm not sure. Anyway, right. So maybe you're thinking, this is a serial driver. Serial drivers are boring. I want a network driver. Well, we also did a network driver. So as it turns out, there are no network driver. There are no network device traits in embedded-hal. I think that's like a for now thing. I think they intend to add them, but if somebody else knows, correct me. Anyway, we ended up using the phi device trait from small TCP, which is the Rust TCP stack that we were porting, which, you know, anyway is what that TCP stack wants to consume. So this is what we needed. And then, like same as last time, we have a handler that we define inside the adapter with a hole, and we say that if the thing that you plug into that hole is shaped like a small TCP phi device, then when you instantiate this, I think I'm mixing up layer 1 and layer 2 a little bit here. I think it probably should have been phi handler. Anyway, yeah, like naming problems aside, the idea is that you end up with a ready-made microkit handler that you can just return from your init function, and indeed that's all the excuse me, all the driver code does. Yeah, so point-to-point phi is a little toy phi that we wrote. It doesn't do interesting things, but the idea is that it's something that implements the small TCP phi device trait, and anything that implements that trait could fit into that slot, and there wouldn't be any difference, because we're only using methods from that trait. And like this is a little bit bulky, I guess. Looking at it, a better design would probably have been to avoid wrapping the handler constructor in unsafe, and instead do the unsafe stuff in all the unsafe is used for is to sort of get pointers to these memory regions. So would have been better to just do that here instead of in the constructor. But point is that it's just a constructor, right? And here we're also constructing the interior phi device, and then in the client. So again, we have the complexity of having to. So like the ETH device is the device exposed to the client, and we have the complexity of having to implement a microkit handler and like speak this protocol that we made up, but this is all in the adapter crate. So again, we only have to do it once. Oh, actually, I almost forgot to mention this. Interestingly, we're yeah. So that ring buffer up there is or those ring buffers are NICs Rust ports of Lucy's zero copy shared memory ring buffer. So I really wasn't doing anything original. Yeah. Anyway. So again, this is all in the adapter crate, and then when you go to use the device in the client, it's just a matter of so this is just instantiating the device again. This constructor could probably be a little simpler, but it's just a constructor, right? And then we use it to do just normal small TCP stuff. So like this is networking code, and the thing to notice about it, I guess, is that it doesn't do anything microkit specific. All of this is just application code that you would be writing if you were writing any small TCP application. The only place where we're using the device is there. So just to do the small TCP poll, which Nick talked about a bit. Yeah. So those are the two drivers that we've played with so far. But there are lots of other embedded-hal driver traits that would be interesting to look at. So that's something that we plan to do if there's time and money. And I guess also an interesting note is that Nick's newer async HTTP server. It didn't make it onto these slides, but I used basically the same adapter crate for that, and everything sort of worked out of the box. So that's kind of cool. Right. So conclusions. I mean, hopefully, super obvious, but maybe kind of useful design pattern. And I guess the takeaway is that, like, this is the sort of low-hanging fruit that can show up when you get to use higher-level language constructs on your embedded code. Yeah, so thanks. That's all I got.
Thank you, Ben. Any questions? So, well, okay, Michael?
Hi, so first, Ben, I believe we also have virt.io example for the driver, for the Ethernet driver.
Yeah. So so that's the async example that didn't make it on the slides.
Okay, and second question, what do you think about having a crate perhaps, or like another library that kind of has these traits and these kind of microkit ready adapters for embedded-hal?
Yeah, that would be exactly the idea. To sort of wrap these existing Rust driver traits in adapter crates.
Okay, we're getting the stop sign, but so as a crypto guy, no OS experience, but Rust experience. So how quickly were you able to come up and actually do something useful?
I don't know how quickly, but let's say weeks.
Okay, and that's a reasonable thing for developers to keep that in mind, that somebody coming in from another domain, it's on the order of weeks. We're not months or longer right now.
No.
And knowing how busy we all are, it's probably not full-time weeks either. So thank you very much, Ben.
Mm-hmm.